Welcome to the next installment of Advanced Chemistry Lectures. This is the 8th lecture in the series on inorganic and organometallic chemistry, and this lecture will target the isolobal analogy, specifically the basics of the isolobal analogy. And so I kind of want to start this lecture by reading this quote that I was introduced to when I was taking organometallics as a graduate student, that no significant line can be drawn between organic and inorganic chemistry. Any distinctions must for the present be merely considered as a matter of practical convenience, calculated to further the progress of students. And so I think that this is really true. We learn organic, inorganic, biochemistry, and physical chemistry sort of as four separate subjects, but they are in fact linked. And the link between the individual subjects and recognizing the link in between the individual subjects really helps, I think, drive research in general. And so what the isolobal analogy will do is form conceptual bridges between inorganic and organic chemistry. And so what we're going to see is that the iron tetracarbonyl fragment is in fact isolobal with CH2. And this arrow right here with the half an orbital below it indicates an isolobal relationship. And so the majority of this lecture kind of summarizes what I believe is explained in Roald Hoffmann's Nobel Prize lecture and a paper he wrote in Science in 1981. And so how are we going to link now transition metal fragments like iron tetracarbonyl to carbenes, CH2? And so what we're going to do is we're going to start with methane. And so if we take methane, the most basic building block of organic chemistry, and we start to strip away hydrogen atoms, we start to actually build fragments that we can then combine to form really any organic molecule we want to. And so if we start with methane and remove one hydrogen atom, we get the methyl radical. If the methyl radical maintains its sp3 hybridization, and a methyl radical is actually sp2 hybridized usually, but if it maintains the sp3 hybridization of the starting methane, if two of these sp3 hybrid radicals get together, you can form ethane, in which the CC single bond is the two carbon atoms are connected by a single bond. This single bond is in fact a sigma bond as well. Well, if we remove two hydrogen atoms now and have a carbene fragment, well, a carbene is a triplet. The carbon atom is sp2 hybridized. There is one unpaired electron in the sp2 hybrid orbital with one electron now in the unused 2p orbital. If these two carbenes get together and dimerize, they can form ethylene, in which the carbon-carbon double bond is composed of one sigma bond and one pi bond. Well, if we remove three hydrogen atoms, we get a carbine. If the carbine has a quartet ground state in which the sp hybrid has one unpaired electron, the unused 2p orbital and the second unused 2p orbital both have one unpaired electron, the two carbines can get together and dimerize to form acetylene, in which the carbon-carbon triple bond is constructed from one sigma bond and two pi bonds. And so between these three fragments, the methyl radical, a carbene, and a carbine, we can build really an unlimited amount of hydrocarbon structures. For example, if an sp3 hybrid gets together with an sp2, we can construct propylene. If an sp2 hybrid gets together with an sp, we can construct phenylacetylene. And if sp3 gets together with sp, we can form alkynes like 2-butene. And so before I really get into it, I want to focus on ethylene, because ethylene involves the construction of a single sigma bond and a single pi bond. And so how does this happen? Well, if we take our two carbene fragments, indicated here as CH2 on both sides, well, remember that the carbon atom itself right here is sp2 hybridized. And so two of the three sp2 hybrids are used to construct the CH bonds. The CH bonds, remember, are constructed from sp2 1s overlap. Well, what that does is leave us with the third sp2 hybrid containing a single electron. Remember, the 2p that isn't used in hybridization also has a single electron present in it. Well, now, if these two carbene fragments get together, the two sp2s can overlap to form a sigma bond and a sigma anti-bonding combination. Remember, a sigma bond indicates that there is no nodes along the internuclear axis. So if I draw the world's longest bond here between the two carbon atoms, notice that there is no change in phase. You have shaded here and shaded here. No change in phase along the internuclear axis means you have a sigma bond. On the other hand, when the two two p orbitals get together, you can form a bonding combination to give you a pi bond and an anti-bonding combination to form the pi star orbital. And so notice here that now it's starting to get a little messy here. Well, maybe I'll do this. The two p orbitals, there's a top half that's unshaded and a bottom half that's shaded along the internuclear axis. If you have one node along the internuclear axis, you have a pi bond. And so the real question is, though, is there a transition metal fragment containing a frontier orbital environment similar to carbene? And what I really mean by this is there is a metal fragment in which you have a singly occupied sigma type orbital and a singly occupied pi type orbital. And so what we're really seeking to do here is replace one of the CH2 fragments with an ML sub X. And so can we take away the CH2 and put in a transition metal fragment and actually have organometallic compounds result from this? And in fact, we can. And so the iron tetracarbonyl fragment is actually isolobal with CH2. And so just like when you had two CH2s get together to form ethylene, you can have a CH2 get together with the iron tetracarbonyl fragment to form this organometallic carbene. And so two fragments are isolobal if the number, symmetry properties, approximate energy, and shape of their frontier orbitals, as well as the number of electrons occupy them, are similar. Not identical, but similar. And so the real question is, well, how do we know then that a D8 ML4 fragment like iron tetracarbonyl has the correct frontier orbital environment? And so what we have to do is we have to start with the building blocks of organometallic or inorganic chemistry, and that's the octahedral geometry. And so if we strip away a single L, we can get an ML5 fragment that looks like the structure in the upper left. If we then remove two of the ligands along, let's call it the Z-axis here, we can then get an ML3 T-shaped geometry. Likewise, if we remove two L's that are cis to one another, we can get an ML4 geometry. If we remove two ligands along, let's call it the Z-axis, we can then get a bent ML2 fragment. And then if we remove three ligands that are oriented in a facial geometry, 1, 2, and 3, along one of the 8 faces of the octahedron, we can get an ML3 geometry that looks like this. And so what we're going to have to do now is first focus on the molecular orbital diagram of an octahedral transition metal complex. And if we do that, we can take something like this chromium carbonyl complex shown here. And so you would actually, in your inorganic textbook, might see a molecular orbital diagram that looks exactly like this. And so when you look at this, many people just say, oh, I'm done. You know, they're finished before they even begin. It looks really complicated. It's tough to parse through what's really going on. And so for the isolobal analogy, what we're really going to want to do is simplify these molecular orbital diagrams greatly. And so the best way to simplify them is to actually go ahead and try to break down the diagram into what forms now sigma bonds and what forms pi bonds. And so that's where we're going to break this down. We're going to form sigma bonds and we're going to form pi bonds. And so what I can tell you is that the lowest 6 orbitals here are the 6 sigma bonds between the metal and the ligand. What we know is the T2G orbitals here are largely non-bonding in nature, and then the upper 6 orbitals here are the anti-bonding combinations. And so what we're going to do now is kind of just take a step back and focus on the d orbitals that are on the transition metal center. And if we focus on the d orbitals that are on the transition metal center, if it's the chromium carbonyl compound showed in the previous slide, we have 3 d orbitals, we have 4 s orbitals, and we have 4 p orbitals. And so if we're breaking these down now into orbitals that can form sigma bonds and orbitals that can form pi bonds, the best thing to do is draw out the orbitals. And so if we draw out the orbitals, they look like they look like the ones that are shown here. And so what I can tell you is that if you have an octahedral compound like the chromium carbonyl shown in the upper right-hand corner, you'll notice that 6 of the orbitals are directly oriented along the bonding axes: the dz squared, the dx squared minus y squared, the 4s orbital, and the 3,4p orbitals. They're directly aligned along the internuclear axis. They're going to form the sigma bonds. The dyz, dxz, and dxy are what I call in the gaps. They're between the metal ligand bonds. If they're between the metal ligand bonds, and notice their symmetry, they're going to be the ones that are going to be able to form pi bonds. And so if we consider the 9 valence orbitals shown here of the transition metal series, 6 of them can form sigma bonds, and 3 of them can form pi bonds. And so let's orient our molecular orbital diagram to reflect that. And if we do that, we arrive at one that looks like this. Notice that we have 6 ligands on the right-hand side. They're going to combine with the 6 bonding orbitals, sigma bonding orbitals on the metal side to form 6 bonding combinations and 6 anti-bonding combinations. Remember that the ligands are all Lewis bases, and so those orbitals are filled, and that results in the 6 sigma bonds that form in an octahedral transition metal compound. Here in the specific one shown in the upper right, we have chromium 0. Chromium 0 is D6, and so those 6 D electrons end up fully populating the T2G, or the pi bonding orbitals, on the transition metal center. All right, and so now we're going to actually have to now alter the MO diagram to reflect transition metal fragments that are now going to bond to organic, let's call them fragments as well. And so we're going to take the exact same approach we did with methane, but it's a little bit different when we're dealing with transition metal compounds. So let's take an ML bond and remove it. If we remove an ML bond to give you an ML5 compound, notice what happens. You're now going to lose a bonding and anti-bonding combination. So rather than having 6 sigma bonding orbitals and 6 anti-bonding, you're going to have 5 bonding and 5 anti-bonding. You're also going to lose 2 electrons because remember that L, the ligand, is a Lewis base. And so now let's look at our transition metal diagram. Notice we now have 5 ligands on the right-hand side, forming 5 bonding combinations with the sigma bonding orbitals on the transition metal center. We now have 5 anti-bonding combinations. Notice that the 6th orbital that could form a sigma bond now has a non-bonding type orbital that's, a little bit high in energy, but you have a non-bonding sigma type orbital, and you have the remaining pi bonding orbitals that started as T2G orbitals. Okay, well, we have now this ML5 fragment. Let's say it's a D7 fragment. Well, if it's a D7 fragment, the pi bonding orbitals are completely filled. However, the non-bonding sigma type orbital now has 1 unpaired electron in it. Well, notice that you have now 1 unpaired electron in a sigma type orbital. Well, isn't that really strikingly similar to the methyl radical? And in fact, it is. The D7 ML5 transition metal fragment is isolobal with the methyl radical. Look at how the orbitals are actually look. Look at this contour diagram. And so here we have a manganese fragment. This is actually 5-. If you look, come down here and look at the key. Is actually a 5- fragment, meaning that it's manganese 0, which is D7. Well, if I take the orbital and actually rotate it by 90 degrees this way, and I take the methyl orbital and rotate it by 90 degrees that way, notice that the overlap would be almost perfect. You could imagine a manganese methyl sigma bond forming, and in fact, it can form. They are isolobal with one another, and so remember what isolobal means. You really have 3 conditions to satisfy. Do you have the same number of frontier orbitals? You do. You have 1 in both cases. Do they have the same symmetry? They do. The proper notation is A1 here, but this is really just a fancy terminology for a sigma type orbital. So they're both sigma type orbitals. Are they of the approximate same energy and shape? Yes, they are. And so what we have really is this isolobal relationship. A D7 ML5 transition metal complex is isolobal with the methyl radical. And you can imagine here now how 2 of these orbitals could line up. They look very, very similar, very, very ripe to form a bond, and in fact is the case. Just as the methyl radicals can dimerize to form ethane, 2 of these ML5 fragments can dimerize to form this manganese dimanganese compound. You can buy this compound, it's very stable, and the manganese ML5 compound can also form a very nice sigma bond to a methyl group shown here. These are all stable compounds. These all really reflect the isolobal relationship between the methyl radical and a D7 ML5 transition metal complex. And so what about the other transition metal fragments? I started by telling you that iron tetracarbonyl is isolobal with a carbene. And so how do we get there? Well, we got to go back to our octahedral geometry. If we go back to our octahedral geometry and now remove 2 cis-oriented ligands, we now get to an ML4 geometry. Well, what's going to happen? Well, we're going to lose 2 bonding combinations and 2 anti-bonding combinations, and we're going to lose 4 total electrons. And so here now is your ML4 diagram. Notice that you have 4 bonding combinations, 4 anti-bonding combinations, The pi bonding T2G set remains totally unchanged, but now you've used only 4 of the 6 bonding orbitals on the transition metal center. They now become 1 sigma and 1 pi bond. And so the question then is, well, how did these 2 sigma type orbitals turn into 1 sigma type and 1 pi type orbital? Well, you're going to have to actually just backtrack to basic molecular orbital chemistry. And so if you go all the way back to H2, remember H2 is formed between 2 hydrogen atoms. Both hydrogen atoms just have a single 1s orbital. If you add them in a constructive fashion, you get a sigma type orbital, that is the bonding orbital. Well, if you add them in a destructive fashion, you form a sigma star type orbital. Well, that sigma star type orbital is antisymmetric in nature. It's out of phase with one another. And so this is exactly what's going on in your ML4 fragment. If you add these 2 together, you get a very nice sigma combination. If you destructively interfere these 2 combinations, they're out of phase. You then get a pi type combination. Well, what you also notice is that this type of orientation, this orbital right here, is the perfect acceptor orbital for an incoming substrate or an alkene. This is also the perfect donating substrate, donating orbitals, excuse me, for an alkene. And so this is the basis of the Dewar-Chat-Duncanson model. Remember, you have a metal. Let's draw a DZ squared orbital that can accept electron density in a sigma fashion from an olefin. The olefin here, this would be its pi bond. In a sigma fashion, no nodes along the internuclear axis. Well, at the same time, as you know, the metal can donate electron density into the anti-bonding orbitals on an olefin. Here is the anti-bonding combination. Donate electron density, and this forms the basis of the Dewar-Chat-Duncanson model you learned about in your inorganic chemistry class. And so that's why these 2 frontier orbitals now, one has sigma symmetry and one has pi symmetry. And now if I go ahead and fill in this MO diagram, let's put 8 electrons like iron tetracarbonyl, the iron tetracarbonyl fragment. Let's insert 8 d electrons. If we do that, notice that the first 6 go into the non-bonding pi-type orbitals. You then have a singly occupied pi-type orbital and a singly occupied sigma-type orbital. Well, isn't this strikingly similar to the carbene fragment? They are strikingly similar, and in fact, they are isolobal with one another. The D8 ML4 transition metal fragment is isolobal with CH2. That means that iron tetracarbonyl is isolobal with CH2. This means that there's no surprise that these 2 fragments can get together and form transition metal complexes. Notice that they have the same number of orbitals, frontier orbitals. You got 2 over here and you got 2 over here. Do they have the same symmetry? They do. One is sigma type, one is pi type, one is sigma type, one is pi type. Do they have the approximately same energy and shape? They also have that. And so there's no surprise now that the D8 ML4 transition metal fragment is isolobal with CH2. And that's no surprise then that this iron carbene can in fact form. And so just how 2 CH2s or 2 carbenes can dimerize to give you ethylene, 2 iron tetracarbonyls can dimerize to give you this iron complex. I should mention that this iron complex is actually not that stable. It's been observed in a matrix, but it is not really isolable. However, the iron carbene complex shown on all the way to the right is in fact stable. And so if this is isolobal with CH2, if you go back to organic chemistry, you can put 3 CH2s together and make a cyclopropane. And so can you put 3 iron tetracarbonyls together to make an all-metal cyclopropane? Well, you can't. You can actually put 2 together. 2 out of the 3 can be iron tetracarbonyl to form a cyclopropane type structure. However, if you go to osmium tetracarbonyl, which is 2 down from iron, it goes iron, ruthenium, osmium, you can take 3 osmium tetracarbonyls, trimerize it to give you an all inorganic cyclopropane. Really quite fascinating. Many people, though, might realize, they might say, wait a minute. Well, I know that the ML5 fragment can also support carbenes. So what's going on? And so if we back up to the ML5 fragment, this chromium pentacarbonyl fragment can support carbenes. And so what is going on? Well, if we actually now take this ML5 fragment, this is chromium 0. So if it's chromium 0, it's D6. That means this pi bonding set is entirely filled. And so this really looks like CH3+. Remember that the Ml5D7 fragment had a singly occupied sigma orbital. There was one electron in this sigma type orbital. However, now that we have a D6 system, there's not an electron there. And so it starts to really look like CH3+. And so that's a little bit weird. If it looks like CH3+, how is it supporting carbines? Well, what we can do is we can take an electron present in one of those pi type orbitals and promote it. If we promote it, notice now what the frontier orbitals look like. You have one sigma type orbital that's singly occupied, and you have a pi type orbital now that is singly occupied. So CH3+ appears to be isolobal with CH2. And so this is known as the deprotonation analogy. Any fragment with CHN+ is isolobal with CHN-1. And so again, this means that CH3+ is isolobal with CH2. And so does this really all make sense? Do all these frontier orbitals match? We know now that CH3+ is isolobal with CH2. That means that the chromium pentacarbonyl fragment is isolobal with the iron tetracarbonyl fragment, and that means that D6Ml5 is isolobal with D8Ml4. And so do their frontier orbitals really match? Well, we know that the D8Ml4 complex has one pi-type orbital and one sigma-type orbital unoccupied, directly isolobal with CH2. We know now that a D6Ml5 fragment, like the chromium fragment, has a fully populated T2G and an empty sigma orbital, and so it really looks like CH3+. However, we take one of the electrons in the T2G set and promote it. If we promote it, then we end up with frontier orbitals in which we have a singly occupied pi set and a singly occupied sigma set. And so with a singly occupied sigma-type orbital and a singly occupied pi-type orbital, we now are isolobal with CH2. And so this is, in fact, the frontier orbitals do match. And so what's really kind of very interesting about this is that what is known is that the iron carbonyl has a really high barrier to iron-carbon bond rotation, consistent with multiple bonding, consistent with a double bond. However, the chromium CH2 fragment rotates easily. And so can we justify this based on the isolobal analogy? And we can. And so the iron compound has a bona fide pi bond. You say the first interaction is sigma in nature, the second interaction is pi in nature, and therefore the bond has restricted rotation. Well, this isn't the case for the chromium carbonyl. There's no conformational preference. And so why is that? Well, remember, we promoted an electron, like so, from the T2G set into the sigma set to give us now an orbital arrangement in which we have a singly occupied pi-type orbital and a singly occupied sigma-type orbital. Well, we just kind of randomly chose one of the T2Gs versus the other two. Well, the second T2G is perpendicular or orthogonal to the d pi orbital shown here. Well, what that means is that the d orbital is in and out of the page. This is the hardest one to draw. That's why I didn't draw it. In and out of the page. Well, the p orbital on carbon can be in and out of the page as well, leading to overlap. And so you only have to move 90 degrees and you can still maintain good orbital overlap. And in fact, this organometallic compound does this. That means that the chromium-carbon bond rotates quite easily, and that's why you see this low barrier. Why in the case of iron, you're locked in place like a normal pi bond. Really very cool stuff. And so we've already done now these two. Can we do the ML3 fragment? And so we can do that. Remember, we're going to remove now 3 ligands that are all facial to one another. And if we do that, we're going to arrive at this C3V symmetric ML3 fragment. And its frontier orbital, or sorry, its molecular orbital diagram looks like this. We have 3 sigma bonding combinations, 3 anti-bonding combinations. The pi bonding orbitals, d orbitals, remain largely non-bonding in nature. They're found right here. Well, just as the 2 in the ML4 case, the 2 sigma bonding orbitals turn into 1 sigma and 1 pi bond. Here, they form into 1 sigma bond and 2 pi bonds. Same method used to do to arrive at these symmetry labels are used as in the ML4 compound. I don't want to go down the rabbit hole, but just know now that we have in our most frontier orbitals, we have 2 pi orbitals and 1 sigma type orbital. And so now if we populate this ML3 fragment with a D9 electron configuration, we arrive at a molecular orbital diagram that looks like this. We have the first 6 d electrons end up populating the T2G type orbitals. We then have a singly occupied pi orbital, well, in fact 2 singly occupied pi type orbitals, and a single sigma type orbital. The relationship is screaming at you. This looks just like a carbine. They are strikingly similar. In fact, not only are they strikingly similar, they are isolobal with one another. And so now, does that mean they have the same number of frontier orbitals, the same symmetry, the same approximate energy? And in fact, they do. Remember the D9 ML3 electron configuration, you have 3 singly occupied frontier orbitals, CH. You have 3 singly occupied frontier orbitals. They each have 1 sigma type orbital. They each have 2 pi type orbitals. The energy of these orbitals is approximately similar, and therefore they are isolobal with one another. And this type of relationship actually is best seen by some really interesting clusters that were formed in the late 60s, 70s, and early 80s, the tetrahedranes. And so the all-organic version is shown right here, but notice how each CH fragment, which are CR fragments here, can be replaced by an ML3 fragment. Well, you can then replace 2 of them with ML3 fragments. You can replace 3 of them with ML3 fragments. And if you drop down the periodic table, rhodium and then iridium, you can actually make an all-inorganic tetrahedrane. Pretty cool stuff. Okay, so we've done 3 of the 5 geometries now. Well, what if we want to look at the ML3 T-shaped geometry? Well, if we start with the ML5 geometry and we remove the 2 ligands along, let's call it the Z-axis here, we get to the ML3 T-shaped geometry. And so how is that going to alter our MO diagram? Well, let's look at the ML5 diagram. Well, first and foremost, if we remove 2 ligands along the Z-axis, we're going to get to that T-shaped geometry. And so what is now going to happen? Well, notice that what that means is that we're only going to have 3 ligands, and so we're only going to have 3 bonding combinations and 3 anti-bonding combinations. What that leaves when we actually delete, let's say, these 2 ligands along the Z-axis, you then have a DZ squared orbital and a PZ orbital that now are going to dramatically change in energy. And how are they going to change in energy? Well, if we're dealing with a first row transition metal element, that's going to be a 3D type orbital, a 3DZ squared type orbital. And so that orbital is going to drop in energy. If we're in the first row of the transition metal series, the PZ orbital is in a 4p orbital. That's going to go way up in energy. And so what we're going to deal with now is a molecular orbital diagram of a T-shaped ML3 compound that looks exactly like this. Notice again, the DZ orbital dropped dramatically in energy. The PZ orbital went way up in energy. If we're now dealing with a D9 T-shaped ML3 fragment, the first 8 electrons populate the pi bonding type orbitals and the DZ squared orbital, leaving us with a singly occupied sigma type orbital. Well, if you have a singly occupied sigma type orbital capable of bonding, we're really looking like a methyl radical here. They are, in fact, strikingly similar, and they are, in fact, isolobal. And so the D7 ML5 electron configuration is isolobal with the methyl radical, which is isolobal with the T-shaped ML3 transition metal fragment with D9 configuration. And so notice this isolobal relationship that's present here. Furthermore, you can go one step farther. Well, remember, CH3 plus was isolobal with a D6 ML5 transition metal fragment, which means that it is isolobal with a D8 T-shaped ML3 configuration. And remember also that the CH3 plus cation is isolobal with CH2 via the deprotonation analogy. And there should be no surprise then that the CH2 fragment, how it very nicely fits into the platinum, the trichloride platinum fragment shown here. That fragment is from Zeitz's salt. It should be no surprise then that an olefin would bind to Zeitz's salt. Really super cool stuff here. And so let's do the final geometry. Well, if we start with the ML2 bent geometry, if we start with the ML4 geometry and remove the 2 ligands along the Z-axis, we're going to be able to access this ML2 type geometry. Well, we're going to take the same game plan we did with the T-shaped. Well, if we have the ML4 fragment, like I just mentioned, and we delete 2 ligands or give the electrons back to 2 ligands along the z-axis, we're going to arrive at the bent ML2 geometry. Now we only have 2 ligands, and so we're only going to form 2 bonding combinations and 2 anti-bonding combinations. Remember that there's 2 orbitals here now that aren't going to be used, the dz squared and the pz. Whoops, pz, sorry about that, pz orbital. The dz squared is going to drop way down in energy to match the other d orbitals that are not engaged in sigma bonding, while the pz is going to jump up in energy because it's, let's say, a 4p type orbital. It's going to go way up in energy. And so when we now look at the MO diagram for an ML2 fragment, again, the dz dropped down in energy. The pz went way up in energy. Well, now notice if we populate this with 10 d electrons, the first 8 go into the pi bonding type orbitals and the dz squared, giving us now a frontier orbital environment with a single pi orbital and a single sigma orbital that are both singly occupied. Well, this really looks like a carbene. This really looks like the CH2 fragment, and in fact, they are isolobal with one another. The ML4 D8 electron configuration is isolobal with a carbene, which is isolobal with a D10 bent ML2 fragment. And so this iron tetracarbonyl is isolobal with a carbene, which is isolobal with a bent nickel 0 fragment, which is D10. And what's really cool about this is we look at this compound right here. This, I think, is really stretching the isolobal analogy out. And so rhodium, the rhodium's in the green box. They are ligated by a CP and a CO that's bridging. The CP is -1. And so each rhodium center in the green box is -1. All right. Sorry, each rhodium in the green box is +1 to balance the -1 charge of each CP. So they're rhodium 1 and D8. Well, if you look at the ML4 fragment in the upper left, you can think of the CP as binding 3 facial sites. And so the CO is then the 4th ligand in that environment. It's rhodium 1. Rhodium 1 is D8. If rhodium 1 is D8 in an ML4 type configuration, you have 1 unpaired electron in a pi type orbital, 1 unpaired electron in a sigma type orbital. You are isolobal with CH2. Well, look at the rhodium now in the orange box. The rhodium in the orange box is a bent ML2 fragment. Notice the overall charge of the complex here is -1, and so that rhodium center is rhodium -1. Rhodium -1 is D10, and so what we're dealing with in the orange box is a bent ML2 configuration that is D10, has the exact same electron configuration as a carbene. It is isolobal with a carbene. You have 1 singly occupied pi type orbital, 1 singly occupied sigma type orbital. All 3 of those rhodium centers are isolobal with CH2. So notice what you're actually looking at here is an all inorganic cyclopropane. Super, super cool stuff. I love this. And so this is really so cool that the Nobel Prize in 1981 was shared by Roald Hoffmann, who got 50% of it, and Fuki, which got the other 50% for their theories developed independently concerning the course of chemical reactions. And so, in part 2 of this series here, or this will be lecture 9, I'll focus on how we can actually use the isolobal analogy to predict the structure of some really interesting transition metal complexes that have been discovered. I hope you learned something. Tune in for the next lecture.